Have you ever wondered how we take something enormous, like a solid boulder you couldn't even budge, and turn it into a powder so fine it can float on the air? This transformation is called size reduction, and it's one of the most fundamental and, surprisingly energy-hungry operations in our entire world.
So that's the big question, right? How do we actually do that? We're going to dive into the raw power, the clever engineering, and some really surprising physics behind this whole process. How do we turn a mountain into dust? Let's find out.
And you might be shocked to find out just how much of your world depends on this. I mean, think about the cement in our buildings, the active ingredients in medicine, the spices in your kitchen, even the powders in cosmetics. It all starts with making really big things very, very small.
Okay, but why go to all this trouble? The real goal isn't just to end up with a smaller piece of what you started with. The real magic, the secret sauce, is what's happening to the material on a microscopic level.
It all comes down to one absolutely crucial idea: creating massive surface area. Think about it like this. You have a single sugar cube, right? It's got 6 sides. Now what happens if you smash that cube into 1,000 tiny grains? You still have the same amount of sugar, but the combined surface area of all those little specks is just enormous.
And that is exactly why this whole thing matters. When you have more surface area, chemicals can react way faster. You can mix different powders together much more evenly, and it even makes it easier in mining to separate the valuable stuff from the junk rock. It is a total game changer.
So, to make this all happen, engineers have basically learned to harness 4 fundamental forces. And what's wild is that every single piece of equipment that does this, from the simplest to the most complex, just uses a combination of these core principles.
The technical name for this whole process is comminution, and it all boils down to these 4 forces: impact, compression, attrition, and shear. All the machines we're about to look at are just different ways of applying these. Let's start with the 2 heavy hitters, impact and compression.
Impact is, well, it's pretty much exactly what it sounds like. It's a sudden, high-speed collision. Just picture a sledgehammer hitting a rock. The rock is sitting still, and bam! This single, fast-moving force comes in and shatters it. Compression, on the other hand, is all about a slow, powerful squeeze. You're crushing the particle between 2 really strong surfaces. The classic example? A nutcracker. See, it's not about speed. It's all about overwhelming, brute force.
Okay, so let's see how these forces get put to work. We're going to start with the absolute giants of the industry, the primary crushers. These are the machines that take on house-sized boulders, straight from the mine.
First up is one of the oldest and most reliable designs out there, and it works exactly like its name suggests, the jaw crusher.
This thing uses pure compression. Rocks get fed into the top, and this massive, moving steel jaw plate squeezes them against a stationary one. As the rocks break, they fall down into the narrower part of the gap, get squeezed again, and keep falling until they're small enough to come out the bottom. Simple, powerful, and it just gets the job done.
Now, for the really big jobs that need even more power and speed, you bring in the gyratory crusher. This is really the next level up in primary crushing.
So inside this machine, you have this big cone-shaped head. It's called a mantle, and it gyrates, which means it kind of does this eccentric wobble inside a fixed outer bowl. As it wobbles, it's continuously crushing material in that narrowing gap between the 2 surfaces.
So here's the key difference. A jaw crusher works on and off, right? It only crushes when the jaw closes. But the gyratory crusher is always crushing material somewhere along its 360-degree rotation. This continuous action means it can just process a much, much greater volume of rock.
All right, so after the primary crushers have done their thing, the material moves on to the finishers. These are the machines that are going to take us from those gravel-sized chunks all the way down to a really fine powder.
A real workhorse for this intermediate grinding is the hammer mill. And this machine is all about brute force and incredible high-speed impact.
Inside, there's a central rotor that spins at an insane speed, swinging these heavy steel hammers. When material enters the chamber, it just gets pulverized. The hammers smash it against a reinforced plate until it's small enough to pass through a screen at the bottom.
And now for the final step. To get that ultra-fine powder we were talking about, we often turn to the ball mill. And honestly, this is where things get really interesting.
Okay, imagine a giant rotating drum, and it's half filled with heavy steel balls. As the drum turns, the balls are lifted up the side, and then they cascade down, creating thousands and thousands of tiny impacts.
But it's also using our other forces. There's attrition. That's the grinding you get as the balls rub and slide against the material. And then there's shear, these microscopic tearing forces that rip particles apart when they get pinched. It's just a beautiful, chaotic mix of forces.
So we've seen the machines and we've seen the forces. But there's a fascinating and pretty critical side to all this power that we haven't touched on yet: energy.
Now, get this. Believe it or not, less than 2% of all the energy poured into these massive machines is actually used to create new surfaces, which is the entire goal of the process. The other 98+% is just lost. It becomes heat, noise, vibration, and friction. It is one of the least energy-efficient operations in all of industry. It's pretty wild.
And yet, for all that inefficiency, this process is absolutely indispensable. It's the unseen first step that takes raw materials from the earth and transforms them into the actual building blocks of our civilization. It's an incredible journey, from the immense to the microscopic.
And all of this leaves us with a really crucial question. This process is vital, but it's incredibly energy-hungry. So as we build a more sustainable future, the great challenge is going to be mastering the science of smashing things, but doing it just a little more efficiently.